Ampacity considerations are very important. The cable ampacity should be determined based on the National Electrical Code rather than the manufacturer's data. National Electrical Code Article 310.15 COIN does not specify ampacities for diesel locomotive single conductors. However, it requires using ampacities established in accordance with the manufacturer's instructions. If specific ampacities are not listed in the National Electrical Code, it is recommended to contact the cable manufacturer for guidance. When addressing the breaker rating and trip unit, a 1400 amp trip unit on a 1600 amp breaker would limit the continuous current to 1400 amps, which may be within the expected ampacity of the cables. Regarding voltage drop, you must ensure that the voltage drop between the source and the plant is acceptable for the equipment at the plant. For ground wire sizing, the ground wire or wires should be sized in accordance with National Electrical Code Article 250.122, which requires a minimum of 1/3 the ampacity of the phase conductors, or at least 25% if the ampacity exceeds 1000 amps. Cost should also be taken into account. Consider the cost of the 1600 amp breaker, the trip unit, and any additional materials and labor required for the upgrade. Here are a few recommendations. First, contact the cable manufacturer for the appropriate ampacity rating of the diesel locomotive single conductor cables. Second, based on the manufacturer's ampacity rating, determine the appropriate breaker size and trip unit setting. Third, consider the voltage drop, ground wire sizing, and costs associated with the upgrade. Some additional notes to keep in mind include: first, if the cables are laid on the ground or covered with soil, refer to National Electrical Code Article 310.15 C2 for specific dirting factors. Second, ensure that the lugs and busbar connections are rated for the continuous current and temperature, usually 90 degrees Celsius. Third, conduct a thorough inspection of the cables and connections to ensure they are in good condition and capable of handling the increased current. When dealing with ampacity, several factors must be considered to ensure a safe and code-compliant installation. The ampacity of a conductor is the maximum current, in amps, that the conductor can carry continuously under the conditions of use without exceeding its temperature rating. This is critical for preventing overheating and potential fire hazards. A National Electrical Code provides tables and guidelines for determining ampacities based on conductor size, insulation type, installation method, and ambient temperature. It's crucial to refer to the appropriate tables in Article 310 of the National Electrical Code, such as Table 310.16 for commonly used conductors. However, in this scenario, standard tables might not directly apply due to the unique nature of diesel locomotive single conductors. Therefore, consulting the manufacturer is essential as per National Electrical Code 110.3b. The manufacturer's specifications should provide the ampacity rating under specific conditions, which must be considered. When conductors are installed in parallel, as is the case with multiple 535 cm conductors, the ampacity is the sum of the ampacities of the individual conductors. However, several conditions must be met to ensure that the parallel installation is compliant. Firstly, all conductors must be the same length conductor material, circular mill area, insulation type, and be terminated in the same manner according to National Electrical Code 310.10h. Secondly, the overcurrent protection must comply with National Electrical Code 240.4, ensuring that the conductors are protected against overcurrent. Dirting factors come into play when conductors are installed in close proximity to each other or in environments with high ambient temperatures. National Electrical Code Article 310.15c provides guidelines for adjusting ampacities based on these conditions. If the conductors are bundled together or placed in a conduit, their ampacity must be derated to account for the increased heat. Similarly, if the ambient temperature is higher than 30 degrees Celsius, the ampacity must be adjusted using the correction factors provided in the National Electrical Code tables. In this particular situation, the conductors are laid on the ground or covered with soil. This installation method is not explicitly covered in the standard National Electrical Code tables, so it is crucial to refer to National Electrical Code Article 310.15c2, which addresses installations in underground ducts or direct burial. The thermal resistivity of the soil and the depth of burial significantly affect the conductor's ampacity. The National Electrical Code provides formulas and guidelines for calculating the ampacity under these conditions, but it may be necessary to consult with a qualified engineer or the cable manufacturer to determine the appropriate dating factors. Regarding breaker selection and trip unit settings, the breaker must be sized appropriately to protect the conductors and equipment. The general rule is that the breaker should not be larger than the conductor's ampacity as per National Electrical Code 240.4. However, there are exceptions to this rule, such as when dealing with motor circuits or when the conductor ampacity does not correspond to a standard breaker size. In this case, the 1600 amp breaker with a 1400 amp trip unit is being considered. The 1400 amp trip unit will limit the continuous current to 1400 amps, which is within the combined ampacity of the parallel conductors, which you mentioned is 1474 amps. This seems acceptable from an ampacity perspective. However, it is essential to ensure that the breaker is suitable for the specific application and that it is properly coordinated with other protective devices in the system. The trip unit setting should be carefully selected to provide adequate protection without causing nuisance tripping. The trip unit's time current characteristic curve should be reviewed to ensure that it coordinates with the upstream and downstream protective devices. Voltage drop is another critical consideration, especially in long conductor runs. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. National Electrical Code Article 210.19 Informational Note Number 4 and Article 215.2 A3 Informational Note Number 2 recommends that the voltage drop on a feeder should not exceed 3% and the total voltage drop to the farthest point of utilization should not exceed 5%. The voltage drop can be calculated using Ohm's law, taking into account the conductor's resistance, length, and the current flowing through it. The conductor's resistance can be obtained from National Electrical Code Chapter 9, Table 8. If the voltage drop is excessive, it may be necessary to increase the conductor size or reduce the load current. Grounding is essential for safety and for providing a low impedance path for fault current to return to the source. The ground wire must be sized in accordance with National Electrical Code Article 250.122, which requires a minimum size based on the rating of the overcurrent protective device. For parallel conductor installations, the ground wire must be sized based on the equivalent ampacity of the parallel conductors. In this case, since the conductors have a combined ampacity of approximately 1474 amps, the ground wire must be sized accordingly. National Electrical Code Table 250.122 provides the minimum ground wire size for various overcurrent device ratings. It is important to note that the ground wire must be properly connected to the grounding electrode system to ensure an effective ground fault path. Costs are always a factor in any electrical upgrade. The cost of the 1600 amp breaker, the trip unit, and any additional materials and labor should be carefully considered. It may be necessary to obtain quotes from multiple suppliers and contractors to ensure that the project is cost-effective. Additionally, the long-term costs of energy efficiency and maintenance should be taken into account. A more efficient electrical system can save money on energy bills and reduce the need for repairs. When considering an upgrade like this, it is best practice to take a systematic approach. Firstly, gather all available information. Collect all relevant information about the existing electrical system, including conductor sizes, installation types, installation methods, and load currents. Obtain the manufacturer's specifications for the diesel locomotive single conductors. Secondly, perform calculations. Calculate the ampacity of the existing conductors, taking into account dating factors and ambient temperature. Calculate the voltage drop and ground wire size. Thirdly, evaluate options. Evaluate different options for upgrading the electrical system, including increasing the conductor size, upgrading the overcurrent protection, and improving the grounding system. Consider the costs and benefits of each option. Fourthly, consult with experts. Consult with a qualified electrical engineer or the cable manufacturer to ensure that the upgrade is safe and code compliant. Obtain the necessary permits and approvals from the local authorities. Fifthly, implement the upgrade. Carefully implement the upgrade, following all applicable codes and standards. Ensure that all connections are properly made and that all equipment is tested before being put into service. Sixthly, document everything. Document all aspects of the upgrade, including calculations, drawings, and test results. This documentation will be valuable for future maintenance and troubleshooting. It is crucial to ensure that all electrical work is performed by qualified personnel who are familiar with the National Electrical Code and other applicable standards. Improperly installed electrical systems can be dangerous and can lead to fire or electrocution. The safety of personnel and equipment should always be the top priority. In summary, upgrading the electrical power to a portable plant requires careful consideration of ampacity, breaker ratings, voltage drop, grounding, and costs. It is essential to consult with qualified experts and to follow all applicable codes and standards. By taking a systematic approach and prioritizing safety, you can ensure that the upgrade is successful and that the electrical system is reliable and efficient. The National Electrical Code is a comprehensive set of standards for electrical installations. It is updated every 3 years to reflect changes in technology and best practices. It is essential for all electrical professionals to stay up to date with the latest edition of the National Electrical Code. The National Electrical Code covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It provides detailed requirements for ensuring the safety and reliability of electrical systems. The National Electrical Code is not a law, but it is widely adopted by local jurisdictions and is often incorporated into building codes. Compliance with the National Electrical Code is essential for obtaining permits and approvals for electrical work. In addition to the National Electrical Code, there are other applicable standards that may need to be considered, such as those published by the Institute of Electrical and Electronics Engineers, the National Fire Protection Association, and the American National Standards Institute. These standards provide additional guidance on specific aspects of electrical installations. It is important to be aware of all applicable standards and to follow them carefully. The information provided in this discussion is intended for general guidance only and should not be considered a substitute for professional advice. It is always best to consult with a qualified electrical engineer or contractor to ensure that any electrical work is performed safely and in compliance with all applicable codes and standards. Electrical systems are complex and potentially dangerous. It is essential to take all necessary precautions to protect yourself and others from harm. Always energize electrical circuits before working on them and use appropriate personal protective equipment. If you are not qualified to perform electrical work, hire a licensed electrician.